Hey guys, welcome to video 100, Work with Varying Force 2. I have a bit of a different intro screen this time because I'm so grateful and happy that you guys have stayed and watched up to video 100. Thank you so much to all you wonderful people for watching and supporting this channel. So I threw in a bit of a corny joke here. Why can't you trust an atom in court? Because they make up everything. So you can laugh privately, and I know no one else will understand that because they're non-physics. But there you go. I hope you guys enjoyed that little picture there. So without further ado, let's jump into the problem. Okay, so work with varying force 2. A spring has K equals 90 newtons per meter. That's the spring constant. Use a graph to determine the work needed to stretch it from x equals 4.0 centimeters to x equals 6.0 centimeters, where x is the displacement from its unstretched length. Okay, so we got to make a graph here, but what are we really looking for here? Okay, we're looking for the work. We know that work is equal to force times displacement. And in this case, the displacement's in the x direction, so we can just say F delta x. Since we're stretching the spring, you can assume that the force is going to be in the same direction, Fx. So really, we're given the delta x here, right? It's stretched from 4 to 6. What we need to find is the force. Now, the force here is called the spring force or the elastic force, and we can represent it as follows. Fs is equal to kx, the spring constant times the displacement. Now we have to make a graph, right? So let's keep it simple. Let's make it a straight line. If you compare this to y equals mx plus b, look at the similarities we have. Okay, so if we make our force along the y-axis, our x is the x, then our slope becomes the spring constant. And that means that the y-intercept is 0. Okay, so we're going to make a graph that looks like that. Okay, so grab your ruler. We know that along the x-axis, the graph has to go at least to 6, so I'm going to go ahead and draw something like that here. Okay, I'm going to draw it up until 7, a little bit past 7, and I'm going to mark, so, oh, actually, you know what? Let's put that in. Okay, so there's my 0, 1, 2, 3, 4, 5, 6, 7. 7, 6, 5, 4, 3, 2, 1, and 0. This is our x. It's in centimeters, so be careful because for these equations you actually have to plug it in meters, so we'll do that conversion after. But for now you can do the graph in centimeters. The y-axis, I don't know the scale yet, but I'm going to just draw an axis here and then I'll figure out the scale afterwards. Okay, but I do know that this is going to be force and that's going to be in newtons. Okay, so let's figure out what our y scale is going to be. Let's figure out the force to extend it 4 centimeters and 6 centimeters. Okay, so F1 is equal to kx1. Okay, our k, the spring constant, it doesn't change based on your extension. It's simply based on the spring itself. Different spring constant. Same spring constant. Okay, so here's where you plug in your SI units. Yeah, x1 is 4.0 centimeters and x2 is 6.0 centimeters. You have to plug that in meters. So 0.04 meters. Okay, so multiply those two together, you're going to get 3.6 newtons, right? Because the meters cancel out. So there's F1. So start to get an idea for the scale. F2 equals kx2, same stuff. 90 newtons per meter times 0.06 meters. Meters cancel and you're left with 5.4 newtons. Okay, so there's about my scale. So let's do this, okay? Let's go up 3.6, that's about here, and 5.4 is about there, okay? So I'm only going to label those 2 points because really I don't need any other points. So there's 5.4, there's 3.6, and of course my 0 is in the same spot. Now, if you don't stretch your spring by any amount, so x is equal to 0, then the force is also going to be 0. Okay, so I'm just going to draw that point in right away. The other 2 points we know is that when it's stretched 4 centimeters, we have 3.6. So let me just draw that point in. I want to be accurate here. So 3.6, of course it's lining up with that. And then when you stretch it to 6, it's 5.4. Okay, so I've got 3 data points. I'm going to connect them and make a straight line. Okay, so there we go. Now we're looking for work. If you guys checked out video 99, work with varying force 1, we actually had a bit of a weird graph, and it had positive parts, negative parts, and we showed that you can find the work by simply calculating the area under the force displacement graph. So if you didn't see that, just check out that video quickly and come back. Okay, but this is the big idea here, that work is the area under a force versus displacement graph. Okay, so make sure you understand that point. Okay, so the area under this graph, we want to know the work to get it from 4 to 6 centimeters. So really we're only dealing with from here to here, that area right there. Okay, so we got to find that. Now that's a bit of a weird shape, but we can break it up into shapes that we know. Okay, so I see a triangle and a square, so I'm going to break it up into those 2 shapes. So if I actually go like that, I've got a triangle and a rectangle, rather. Okay, so I'm just going to connect these points so it's more visible. So that x corresponds to this force. This x corresponds to that force. Okay, so let's find out what these 2 equal. Okay, so essentially the shape we're dealing with here is this. Okay, so let's call the top 2, let's call the bottom 1. So the work to extend it from 4 to 6 is equal to area 1 plus area 2. Okay, so the area of 1, it's a rectangle, right? So it's going to be base times height. Be careful, again, the graph is in centimeters. If you actually made your graph in meters, that's a really good idea. So go ahead and do that. Otherwise, make sure you plug that in. The base of that is 2 centimeters or 0.02 meters. Okay. The height of this rectangle is 3.6. So that's area 1. Area 2, the base is the same. It's 0.02, but this is a triangle, right? So it's 1/2 base times height. The base is the same as the rectangle, 0.02. The height is 5.4 minus 3.6. Okay, so just punch that in your calculator. This first part here, when you get it, you're going to have 0.072. The second half over here, you're going to get 0.018. So when you add those 2 together, 0.072 plus 0.018, you're going to get 0.09. Okay, so the work done to move it from 4 centimeters to 6 is 9.0 times 10 to the minus 2 joules. And there you have it, guys. That's it for this video. I hope you enjoyed it. Again, this is video 100, super special. So thank you so much for your continued support. And be sure to let your friends know if they struggle with their physics homework too. All right, guys. Be sure to check out video 101, Work Energy Principle 1. Next video posted tomorrow or next day at noon, depending on what day of the week this is. All right, guys. Talk to you later.